Okay, in the last lesson we looked at static electricity, which involves charges staying stationary or still on an object. So to get real electric circuits going on, we need to get the charges moving around in some sort of a circle. So circuit basically means circle. So the sort of requirements you would have for that is you would need some sort of a battery or dry cell here. So I'm just going to draw that, that's your positive terminal, there's your negative. You would connect it with some sort of a conductor or wire to some sort of a globe or output device to use the energy up and then back into there. So that's a really simple one without a switch or anything. Now obviously when you've got very complicated circuits like in computer systems or even videos or wherever else, you would need to have a better way of doing it than this, where you draw a diagram of it, because that takes ages. If you can imagine having, say, the 20 globes in the household plus switches plus everything else, it's going to get very messy and the curvy lines don't help. So instead of that, they tend to use symbols here to indicate what the electrical circuit is like. Okay, so typical ones you can use here would be a simple one for a cell, which has just got a positive terminal and a negative terminal there. If you start to put them together, you can get what's called a battery, where you get more than one cell together. If you indicate that with an arrow going through it, that often means it's adjustable, the sort of thing you would get in a power pack, okay, or power supply. And typical globe diagrams would be something like that, with a circle and a cross in the middle of it. Sometimes they used to draw them like this, with a circle going around as a globe, but that's your globe or a bowl. All right? And a simple wire would be like as a conductor. It would be a line. So that would indicate a conductor, which actually conducts electricity. Other ones you might use in the circuit is you might have a switch that is closed, which actually lets the power go through, and you can also have one that's open there, which would turn the thing off because it's got a gap in the circuit, and so you won't get electricity flowing around there as a complete circle. So they're the switches you can get as symbols, open and close, or close and open in this case. And so this would be the on one, and this would be your off one. You might decide to measure the current going through the circuit, in which case you use an ammeter to measure the amps. That's an ammeter. And you could also measure the voltage or potential difference in volts using a voltmeter. So they're the typical ones you might use. You may also include a resistor in the circuit there to protect the items. Sometimes it has a number attached to show you the resistance. And you can also get variable resistors which can be adjusted, which they would use in dimmer switches there. And so they're the sort of typical components you would use. So based on that, you would draw that circuit completely differently then. You would just have to draw a simple cell here, negative and positive, going to a globe and back to the other side of the cell, and that's a much faster way of doing it. It's neater, and as I've said, as they get more complex, it's much better to do it that way. Okay, now one of the earlier things you can do is actually sort of test materials to see which ones conduct or not. So you can set up a circuit to see which ones are conductors and which are insulators. So I would go and get a power supply of some sort, set it on maybe about 10 volts there, go and put a globe in there to see if it goes bright or not, put an ammeter alongside to measure how much current's coming through there, and have some contact points there where I can put different stuff in there. So you might try different metals into this position, like copper or brass or lead or zinc or bronze or tin or silver or gold or whatever, and see if they conduct or not. And by and large, you're going to get a very bright globe there when you do that, and you're going to get a good strong current there. So let's say you get 1 amp coming through there. And that'll be a typical result we get for metals in there, because they will complete the circuit and the electricity will flow around continuously from one side to the other. So if we do it by the conventional current, it'll actually flow around through the circuit, down through the actual object there, and the other side. Okay. If you were to try something else though, and you put, say, some non-metals in there that might be insulators, and you were to try something like some plastic or some rubber or wood or cardboard or so on, you'll find these are insulators. So these are non-conductors, and you would find that the globe doesn't go on at all, and that needle would actually read 0 amps. Okay, so you'll get nothing there as a result. And then insulators or non-conductors. You can get ones in between that are sort of semiconductors here. So if you try something like pure water in place of this, and I normally just get a beaker of water there and place the 2 leads into a beaker of water there, and you put those leads into there, you'll find that pure water on its own doesn't virtually conduct nothing at all, especially at this voltage here. Higher voltages, it becomes extremely dangerous, by the way, but at this low voltage you're going to get virtually no reading on the ammeter. if you start to add some salt in this and stir it up, you will find that salt separates into sodium ions and chloride ions, and you've now got some charged particles that can flow across this here and carry the electric current around. And you will start to get this reading starts to go up. So it won't start at, it may start at 0, but it will actually start to rise there. And if you put enough in there, you can actually get this to conduct quite well. And so that's more of a poor conductor, depending on how much you have in there. So there's a bit of a range there. So there are three things to consider when you look at all electrical circuits. It's based on what's the voltage doing in there, what is the current doing, and what is the resistance in the circuit. So they're the three concepts you need to get across in your understanding to sort of work with this well. So what is the difference between the three of them? We can look at an analogy to sort of try and help this here. So there's a couple ways of looking at this. If you've seen the Van de Graaff generator spark, when you've got something connected to the earth there, Van de Graaff generator, you can get sparks flying across here. Now the length of the spark will give you an indication of the voltage or potential difference. And the reason for that is that voltage here really tells you how much energy is being supplied per coulomb of charge. So to each of the charges, how much energy they're getting as a kick. Okay? So if you're told here that you had, say, 100 volts there, that would mean it's getting 100 joules of energy to every 1 coulomb of charge. Okay? And it actually has a formula for that. The voltage is the amount of energy supplied per quantity of charge. So that's the formula. Okay? And in this case, it'll be indicated by the length. So the longer length of the actual spark, the greater the voltage has to be. And it turns out you need thousands and thousands of volts to sort of jump the distance that you see in a Van de Graaff spark. Okay? The current is different to that. If you look at current here, the amount of current that's going on, that's based on the thickness of the spark, if you like. Because that'll give you an indication of how much charge is flowing per second. So I guess it's the thickness and the speed to some extent, but in this case the speed is fixed. So if I was to see a much thicker spark going across here, I would be more worried, because it would mean there's a lot more charge flowing per second across here. So if it was a very thick spark, it would mean there's a lot more charges flowing per second, and the current would be higher. So again, there's a formula for that one you can consider, and the formula would be the intensity of the current here, I, intensity of current, is the quantity of charge in a given time. So rate of flow of charge. Okay, so it's how many coulombs per second. And rather than being measured in volts like the voltage is, this is measured in amps after ampere, Andre ampere. Okay, so that should give you some indication of those two. Now, there's a way of actually doing this in terms of water as an analogy. This is very similar to how a circuit would be set up. So I've just got a fountain here, and the water's going to be pumped from the pump here, pumped up through the actual piping, through Fred's body, out through the hand and through this little holder that he's got, and you've got a spray of water coming out the top here, and you should be able to see that coming out the top. And it's just spraying down and going down, and hopefully back into the fountain. You will lose some water. This will complete a circle because the water will then be sucked in from the pool and back into the pump. Okay, so you have got a complete circle here, and the energy source is the pump. So this is very much like a circuit would work in terms of an analogy. The pump is representing the battery, or the energy source, the power source for your circuit. The water is representing your charges flowing around your circuit there. And obviously there's got to be some place to use the energy. In the case of the fountain, it's the fountain coming out and being pushed to a great height here, whereas in the case of the circuit, it's the bulb. Alright, so there's your energy being used there. So if you go back a step then, how is this the same? The voltage here is supplying energy to the charges to push them around the circuit. Okay? The pump is going to supply energy to the water, or pressure to the water, to actually push them around the circuit and get them to go high into the air. If you were to turn the actual pump up and use a higher pump there, a stronger pump, so you had something with more voltage, say, in terms of analogy, if you went from 12 volts to 24 volts here and supplied more energy to each charge or more energy to the water, what would the result be? Well, in the case of the fountain, the water should go with more energy, it should go faster and go with a higher movement there. You should see it's got more energy, the fountain should come out higher, right, to a taller height against gravity. In the case of the electrical circuit, we would expect this bulb to be glowing brighter for the high voltage. And in fact, if you make the voltage too big, you could blow the globe. All right? So voltage and energy, you've got to think of being the same sort of things. Okay? It's how much energy is supplied to the water or how much energy is supplied to each coulomb of charge. Now, if you now consider the current that's going around here, the amount of water going past per second in this case here, you could measure it in litres per second, the water current there, litres per second. But it's basically an amount divided by a time. In this case here, it's the quantity of charge in a given time. Okay, coulombs per second, and that's what amps is. So, how many charges pass a point per given period of time, rather than how much water passes per period of time. If you were to raise the pump up like you did before from a small pump to a larger pump, or in the case of battery 12 volts to 24 volts, what we would expect to find is, yes, the energy does go up, as we've said before, but you also get the current going faster. If you put a bigger pump here, it's going to pump the water harder and faster, and the water's coming out the top faster. Now that means the rate of flow of water current is going to go up naturally. So obviously the two are linked, and that's why people confuse them. The voltage and the current generally link together. If you increase your voltage, you usually get a higher current correspondingly. All right? And the same will happen with the circuit here. I would expect the current here to go up if I was to change that battery and put two of them in there. This is actually not a battery, it's a dry cell. Just to realise that. It's only got one positive terminal and one negative one. So it would have that symbol there. They should be using the term cell there in my circuit diagram there. So that should give you the difference between the two of them. So one last thing here, if you start to use your analogy to talk about resistance then, the resistance. Now that obviously comes from the word resist, or how much it holds back or slows down the current. Something with a really high resistance would obviously reduce the electrical current that's going to go on. So you would expect current to go down. So if we did have an insulator in there which had an infinite resistance or very close to it, your current would be virtually zero. In this particular case, could you change the current that flows around in this piping here without changing the pump? Well, yes, you can. If you use piping that's actually thicker or thinner, that will change the effective resistance to the water flow down the pipe. Okay, so thinner pipes would allow the water to flow more slowly, or cause the water to flow more slowly with a lower current. The current would go down if it was thinner. Okay, and that actually happens the same with electrical wires. If you were to use a wire with a small area of cross section here, there would be less charge available to flow down that wire, and the current would be actually a lot lower. And whereas if you have a wire that's thicker, you'll actually find that you've got more charges available down that wire, you'll get more current flowing down there because you get more charges per second. By the way, longer wires will tend to actually have more resistance as well because they're harder to flow through.